Okay, so this is going to be a relatively brief, hope brief, fairly simple introduction to energy, work, and power. And those are all words that I know you've heard before, and you may have certain ideas of what they mean, but remember when we get into physics, a lot of times there are words that seem to be familiar to us, but in physics we define them slightly differently than what we're used to sort of in our normal lives. So you may have a definition of these, but I think it's going to change a little bit. Energy is really important to understand. It's actually the most central concept of all of physics. Everything in this planet, everything in the universe, and everything we talk about in this class can and does relate back to the concept of energy. So let's talk about energy first, and then we'll get to work and power. And those three concepts may not seem related to you, but in the next part of the course, we're going to understand that they are very closely related, very, very closely related. So let's talk about energy. There are actually three definitions of energy. We're only going to talk about two right now. So definition number one, energy is the ability to produce change in an environment. And that sounds like almost a biological definition, and indeed it is. If an organism wants to live, it's going to have to find a way to modify the environment it lives in to some extent in order to make its chances for survival better. But you can't do that unless you have energy. So energy is the ability to produce some sort of change in an environment, some way to change your surroundings, the ability to move. Well, that actually comes in the next one. But the point is, definition number one is a biology definition. In case you weren't aware, this class is not biology, this is physics. And so definition number two is the one that I really want to focus on here. And energy is the ability to do work. Very simple definition, but it's a very profound definition, as we'll see later. And we'll define what exactly work is in a minute. But energy is the ability to do work. In the previous video, when we did the work at the People Power Lab, where you did some work to walk up the stairs, the only way that you could do that is if you had energy. So energy is the ability to do work. Unit for energy, all energy, is joules. You may recognize that from chemistry. It's named after chemist James Joule. Capital J is the abbreviation, but all kinds of energy are measured in this unit. Heat energy, light energy, electrical energy, all kinds of energy is measured in joules. There are lots and lots of different kinds of energy. But today, to start with, just to understand the concept of energy, we're just going to introduce two kinds. And that's kinetic energy and potential energy. You may have heard both of these words, and let's make sure we understand what they are. Kinetic energy is specifically the energy of an object due to its motion. So very simply, that means that any object that is in motion, that is currently in motion, has kinetic energy. A lot of times in science, when we look at prefixes and suffixes, the meanings of those help us to understand what the word means. And this prefix, K-I-N, you may have heard that if you go to college, you can major in kinesiology. Maybe some of your coaches were kinesiology majors. Kinesiology is the study of things that involve movement, namely sports. So kinetic energy is the energy an object has due to its motion. If you're not moving, you have no kinetic energy. The other kind of energy is potential energy. Potential, you can think of that as just basically energy that is stored up, that is not currently being used. And both of these types really, we can kind of put a circle around both of these, and we're going to call them both mechanical energy. Mechanical energy is energy of motion, or energy that can produce motion, stored energy that can produce motion. Now, there are lots of ways to store energy, just like there are lots of ways to store, things in your house. Lots of different types of potential energy. We can have chemical potential energy is a good way to store energy. For instance, when you eat your lunch, you're taking in chemicals, and in those chemicals, the potential energy to do the things that you need to do is stored, because from those chemicals, you can make the most important chemical in your body, one of the most important chemicals, which is ATP. ATP is the chemical, the energy currency of the cell. And in that molecule, you have chemical energy stored as well. That's potential energy, but we're not going to get to chemical potential energy today. In a bowstring, in a slingshot, in a trampoline, we have what's called elastic potential energy because those things stretch, and when they stretch, they're storing energy because they're not moving yet. But if you let them go, if you let them move after being stretched, they will produce motion because there's energy stored in those things because they're elastic. But the thing we want to talk about today is called actually gravitational potential energy, and we'll get to that in a minute. That's the energy you have when you're on a cliff or in a tree or up on a desk at some height above the Earth's surface. You have gravitational potential energy. And the reason for that is because of the force of gravity, you have the potential to then fall. So it's gravitational potential energy and kinetic energy that we want to talk about specifically today. There are formulas for both of these, as is the case in a lot of the course. Kinetic energy has a really cool sounding formula. Ke stands for kinetic energy, and the formula is mv squared over 2. You might hear this in some circles as 1/2 mv squared. That's the way I learned it. I've done it this way because I think it helps most students to understand how to calculate kinetic energy by doing mv squared over 2. It's the same equation. Multiplying by 1/2 is the same as dividing by 2. But we've seen all of these variables before except for kinetic energy. That's our new one. It's measured in joules. M is mass, always has to be in kilograms, and V is speed in meters per second. Notice here, really important to notice, this squared. Remember our PEMDAS. So we got P, E, sorry my writing isn't that great because I'm trying to use a mouse, M, D, A, and S. Really important to understand that this tells us how to do arithmetic from left to right. P stands for parentheses. That means do anything inside parentheses first. And we're not going to have that in this equation because we see no parentheses here. And you might get confused about that because when I plug numbers in, I do tend to put them in parentheses. But there's nothing to do inside this parentheses. There's no mathematical operation. It's just a placeholder for us. The E stands for exponent. So we're going to do this exponent first. The first thing we're going to do is to square this V. And the squared only applies to the V here. It doesn't apply to the mass. We don't multiply these two together first. That's the next step. So the first step is to take care of the exponent by squaring the V. The next step is multiply, divide. This step actually can be done at the same time. Multiplication and division are opposites of each other, so you can really do them at the same time. So after we square this V, it's not going to matter whether we divide by 2 next or multiply by the M. It doesn't really matter there. That step can be done all at the same time. And there is no add, subtract in this one. A stands for add, S stands for subtract, but that would be the last step in the formula. So that's the kinetic energy formula or equation. The next one is going to be potential energy. And again, it's gravitational potential energy that we're dealing with specifically today. Objects store gravitational potential energy when they are held at some distance above the Earth's surface. And it's pretty simple. The equation is PE, which stands for potential energy or gravitational potential energy, equals mgh. Yet another equation that is very easy to remember. M is mass, once again, in kilograms. And the one that we want to make sure to focus on today is this one. We've had it before. We've had it before in an equation that looked like this. Maybe you'll remember. Fg equals mg. All right. And g, lowercase g, is the acceleration due to gravity, which is on this planet, negative 9.8. But notice the yellow here is highlighted positive. We're going to talk about that in a second. And then h is at whatever height this thing is above the ground, and that has to be in meters. So PE equals mgh is the equation for potential energy. Now let's talk about that positive. Now some of you might remember, wait, Mr. Valls, you said G always has to be negative. Yes, but when we get to energy, it's really important to understand that we always like positive energy. This is a good thing to remember. Nobody likes people with negative energy. I don't want your negative energy. We like positive energy. Energy has to be positive. And the reason why energy has to be positive is it's not a vector. Remember, we have vectors and we also have scalars. Scalar quantity is a quantity that does not have a direction. For instance, mass. Mass doesn't have a direction. Vector quantities, however, have a direction, like force, like displacement, like velocity. We had to report direction with those. Well, energy is not a vector, it's a scalar quantity. Energy doesn't have a direction. It makes no sense to define energy with a direction because it's simply an amount. It's not a vector, but it's a scalar quantity. So it cannot be negative. If it was negative, that would indicate direction, and that's not possible. So energy always has to be positive, and for that reason, we're going to use positive 9.8 instead of negative 9.8 for the acceleration due to gravity. So it's just with energy. That's something that you just have to kind of memorize and know that we're going to use positive 9.8 for gravity. So let's look at some of these practice problems with energy together. So solving problems with energy is actually pretty simple, as you may have been able to see by these equations. Again, kinetic energy we said was mv squared over 2. Potential energy is mgh. Any problem that we do is always just as simple as the guess method. Remember, the given, the unknown, write the equation, and then substitute and solve. So this says we have an 875 kilogram car that is traveling at 44 meters per second while passing another car. How much kinetic energy does it have? So when we read this problem, we should first of all just think about the guess method and go, what is it giving us? What are the givens? Well, we have 875 kilograms, which is the mass. Maybe we'll get this just a little bit closer here. 44 meters per second is our speed, which is v. Now remember, some of these things you do have to take some time and just memorize. Memorize the variables, which are the letters that we use to represent these things. Memorize the units, which is the letters that come after the quantity, which is how we measure that thing. So they give us the mass and they give us the speed. There's nothing else that's given here. And it says how much kinetic energy does the car have. So our unknown, our U step, is kinetic energy. We're looking for KE. Right? And it's fairly simple. The equation here that we're going to use to find KE is the KE, kinetic energy equation, 1/2 or mv squared over 2. Again, may seem very simple and stupid at this point, but we want to make sure to have the stepwise process down so that when we do more difficult problems, the process can help us because we know it. So the last step, we're going to substitute the numbers we have into the equation and then solve it. So in for mass, I put 875. KE is what I'm trying to solve for, so I'm going to leave it the way it is. KE equals mass is 875. Put that in parentheses just because it helps it to look better. V is 44. That's got to be squared, and the over 2 there. Now remember PEMDAS. Squared only applies to the V, and this is the first thing we have to do. You have to square the 44 first. If you do that, the 875 stays the same because the 44 is the only thing that gets squared. 44 squared is 1,936, 19 squared. Put your 2 on the bottom. And now we can multiply and divide, and it literally does not matter what order we do this in. You can do that times that divided by 2, 875 divided by 2 times 1936, 1936 divided by 2 times 875. It does not matter. You can do any of that, and anything, if you do it correctly, will get you 847,000, and this is energy. The unit is joules. So this car is moving at 44 meters per second, and when it's doing that, it has 847,000 joules of kinetic energy due to its mass and due to its speed. Notice here, really important point, since the speed is squared, the speed definitely has a greater effect on the kinetic energy than the mass does. The mass certainly has an effect. It's in the equation. The greater the mass, the greater the kinetic energy. But speed has a much greater effect because the speed gets squared in the equation. Don't ask me why that is. It just is. Second problem, 50 kilogram ball is shot from a cannon to a height of 425 meters. How much gravitational potential energy does it have? Just a different problem. So same thing, guess method. We have our mass, which is 50. It's shot to a height of 425 meters. That will be our h height. Now you could put distance on this, but the problem says height. It's important to recognize that, especially when we're dealing with what the problem is asking for, gravitational potential energy. Remember that there's no D in this equation. It's actually an H for height. But it is a distance. It's just a special vertical distance. So our unknown here is potential energy. Our equation, PE equals mgh. So I'm going to substitute and solve now, leaving PE because that's what I'm looking for, substituting these numbers into this equation. M is mass, that's 50, and then people get to this point and they go, oh wait, the problem didn't give us G. It's never going to. Remember, G is that thing that you're just supposed to know. G was, hopefully you have this written here, positive 9.8. It's got to be positive because we like positive energy. So remember, when you see G, just throw 9.8 in there. It will never be actually given to you in the problem because you're expected to know that. And the height is 425. This just became really, really stupid simple, and it doesn't matter what order you put it in. You simply multiply those three together, and you should get this. 208,250 joules is the potential energy there. So just some really simple practice running these numbers. We're going to do one more here. Why don't you do this one on your own? Pause the video and do this one on your own and see if you can get it, and I'll come back and do it with you. All right, so let's see if you've done this. It gives us the kinetic energy of the player right here, which is different than the previous two. Has that much kinetic energy while running at a V at a speed of 10 meters per second. And we want to know mass. So same thing, we're going to go a little bit faster. Kinetic energy is 550. We know the speed is 10. Problem wants us to find M, the mass. This is such an important step because as long as you can write down the variables, not just this number, if all you write down is the number, you haven't done much for yourself. You need to know the variables, the letters that represent these quantities in the equation, because it's the E step, it's the equation that we have to come up with. And if you don't know the variables for what you're given and what it's asking for, it's harder to find the equation. Now all I have to do is find an equation that has all this stuff in it, and it is KE equals mv squared over 2. Now remember, we may be asked to solve for things in this equation that are not necessarily out front here. In this case, we're solving for m. So now we're going to substitute and solve everything into this. KE is 550. Mass, I'm going to leave it the way it is. Don't put an X, don't put a blank, don't put a question mark. Leave it M, because that's what we're looking for. Our V goes in as 10. Leave the squared, it's part of the equation, over 2. Now we got some simplification to do. Remember PEMDAS, exponent is the first thing we do. So we have to square this 10 first. 10 squared is 100. Just kind of my notation. You don't have to do it this way. But this problem happens to be fairly simple. If it was a different number here, like we squared 44 up here, I don't know that off the top of my head. I might like to do that in the calculator and write another step right here. But in this one, it's fairly simple. 10 squared is 100, and then we can do this divide here now. 100 divided by 2 is 50. So what we actually get here, we can rewrite this, is 50 m. Now all we have to do is divide by the 50 because we're going to do the opposite operation. These are multiplied, so we divide to get rid of it on the right side, and 550 divided by 50 gives us a mass of 11 kilograms. So that's how we work problems with energy.